In the last lesson, we learned two algebraic tools to help us work with logarithms. We learned the power law of logarithms, which is very much related to the power law of exponents. And we also learned the change of base formula to help us evaluate logarithms if they weren't a base of 10, or they didn't have a base of 10. In this lesson, though, we're going to learn two more tools to help us work with logarithms. We're going to learn the product and quotient law of logarithms. Now, in the previous lesson, I also said that these logarithm laws are very much related to the exponent laws that you learn in grade 9. So I spoiled the laws by not only by writing out what they are, but giving you the name, product law of logarithms. So hopefully you remember the product law of exponents because they're very much related. The product law of exponents states that if you multiply two powers with the same base, you add the exponents. Okay, so if you look closely, you can already see that they are related because exponent, logarithm is an exponent, logarithm, so you're adding the two exponents. So it's already seeing, hey, it's very similar to what you did in grade 9. But anyways, I will prove to you the product law of logarithms. So this is the product law of logarithms. I'm going to try to prove it. If this was in a classroom setting, I'd just give you 10 minutes or 20 minutes and let you try to prove it yourself. Okay, so I'm going to let x equals log base b of m and let y equals log base b of n. So this is in logarithmic form. I'm going to write it in exponential form. So b to the x is equal to m, and b to the y is equal to n. Now, because this is the product law of logarithms, I see two exponents. I'm just gonna multiply. Sorry, I see two powers. I'm gonna multiply the powers. B to the x times b to the y, which is equal to m times n. Correct? B to the x is m. B to the y is n, so b to the x times b to the y is obviously m times n. And it's funny because we're going to use the product law of exponents to help us prove the product law of logarithms. Right? When you multiply two powers of the same base, you add the exponents. And now I'm going to re-express this in logarithmic form. So log base b of mn equals x plus y. But wait a minute, what is x and what is y? Well, x is log base b of m and y is log base b of n. And there you go. That is the product law of logarithms. So what it's really saying is that if you have two logarithms, if you're adding two logarithms with the same base, if the base is different, this won't work out. So if the bases are the same, then you can express it as a single logarithm. It allows you to express a sum of logarithms as a single logarithm. Okay. And it makes sense because think about it. If this is exponent, this is exponent, okay, you're allowed to add the exponents as long as you're multiplying the powers. M and n are the powers. So if you're multiplying the powers, of course you're allowed to add the exponents. Now conversely, which you learn in grade 9, or not conversely, but on that note, you learn the quotient law of exponents in grade 9, which is if you divide the powers, if you divide powers with the same base, you subtract the exponents. Okay, so I'm very tempted to not show you the proof because it's pretty much identical to what I just wrote, except instead of multiplying here, I'm dividing, but I'll write it nonetheless. So I'll skip the step because x and y is still the same. So I'm going to write b to the x over b to the y, which is equal to m over n. And funny enough, again, you use the quotient law of exponents to prove to yourself the quotient law of logarithms. Isn't that nice? So really, it's exactly the same, except for here, the big difference is instead of multiplying the two powers, I divide it because I'm trying to show you that you want to subtract the exponents. Anyways, the quotient law of logarithms states that if you are subtracting two logarithms with the same base, you can once again express it as a single logarithm, but the arguments are being divided instead of being multiplied. All right, I think we're good to go. Oh, I forgot, restrictions still hold. M is greater than 0, the arguments are greater than 0, and the bases have to be greater than 0 and not 1, of course. Okay, so that's pretty repetitive. We've been talking about those same restrictions for quite a while now. Okay, so write as a single logarithm using the product law of logarithms. Okay, so this is same base, so 3 logarithms all same base, so I can simplify it to a single logarithm just by multiplying the arguments. 6, 288. Okay, so here add, subtract, so and of course all base 10. Always double check that the bases are the same, because you're not allowed to use the product law or quotient law of logarithms if the bases are not the same. So this is going to be 3x squared y over 2y. Simplify that, so you get 3 over 2x squared. Let's put in brackets so we know that it's not log of 3 over 2 times x squared. Okay, so state restrictions. Because x cannot be anything you want. This logarithmic expression only makes sense if x is greater than 0. Okay, so from here, it's that I know if you look down here, you can say x could be -6, but if you look at the original expression, x must be greater than 0. And y must be greater than 0 as well. Okay, the argument must be positive, because you cannot you can't have a negative or 0 argument, because if you think back to powers, you can't have a result being negative or even 0. Okay, you can think about the exponential function as well. So there's a lot of different explanations, but really try to understand why the argument has to be positive. Okay, because that is a big idea in this lesson. Okay, nice. Some nice evaluating questions. So of course you can just punch in your calculator and do all the work, but on the tests we may not let you have a calculator. So 4 times 16, I can use the product law of logarithms because the bases are both the same. So 4 times 16 is 64. So 8 squared is 64. Okay, quotient law of logarithms. They both have a base of 3. So 405 over 5 is 81. And it's 4. 3 to the power of 4 is 81. Over here, let's apply the power law of logarithms. Then I apply the product law of logarithms. I can't apply the product law right away because of the half and the 2. But no problem. Easy fix. So 5 squared is 25, root 16 is 4, so this becomes log 100 because 25 times 4 is 100, and oops, it should be 2. 10 squared is 100, so log 100 is clearly 2. Alright, let's keep going. Log base 2 of 3 plus log base 2 of 8 minus log base 2 of, I'm just going to write 6 because half means power law of logarithms, so it's a power of 1/2. So 36 raised to the power of 1/2 is the square root of 36, which is 6. So product law and quotient law. I can do it because it's base 2, base 2, base 2. Really check the base. Sometimes they are different. Okay, so this is 24 over 6, which is 4, which is 2. Okay, log base 2 of 4 is obviously 2. Alright, now instead of expressing it as a single logarithm, you want to break it apart and express as a sum or difference of logarithms. So this one here, log base 3 of x plus log base 3 of y. Restrictions. Now you can break it apart, but now if you write it like this, x has to be greater than 0 and y has to be greater than 0. Here, so the numerator is uv, so it's log u plus log v, and since the denominator you're dividing by root w, so it's minus log root w. Simplify even further by using the power law of logarithms. So restrictions. So u is greater than 0, v is greater than 0, and w is greater than 0. Please don't get in the habit in saying it's always just greater than 0, because you'll see later on in some examples, it's not as simple as just greater than 0. Right now it's just greater than 0 because the arguments are just u by itself. It's just a variable by itself. It's not that complicated. But as you can see, like down here, it's 2x minus 2, x squared minus 1. So then you have to really think about it. Okay, simplify and state restrictions on the variable. So over here, there are a few ways to do this. I'm going to do the easy way. Power law logarithm. So 3 over 2 log x plus 2 log x minus half log x. So it's just basically like collecting like terms now. 3 over 2 plus 2 minus half. So that's 1.5 minus half is 1, so 1 plus 2 is 3. 3 log x. Restrictions. X has to be greater than 0. Alright, so here, log of 2x minus 2, you know what, I'm going to factor that, and x plus 1, x minus 1. So, common factor of x minus 1. So that part, I would argue, is the easy part to the question. Just simplifying, okay? You should be very good at factoring by now, spotting the common factor, difference of squares. That part is the easy part. The hard part is stating the restriction. So I'm going to help you out. So for this one, for 2x minus the argument of 2x minus 2, I'm going to draw a number line, okay? And I'll explain to you why I draw a number line in a second. But I'm going to use this number line to show me when is 2x minus 2 positive. So you want the factor x minus 1 to be positive. So that's pretty easy. X minus 1 is positive when x is greater than 1, right? X minus 1 is positive when x is greater than 1. But what about the denominator? That one's a little trickier, because you have a quadratic. What you can do is think of the parabola, okay? Sure, you know what, let's add even a diagram for ourselves. That parabola is opening up and has x-intercepts at -1 and 1. So if you look at the parabola, this product will be greater than 0 when it's greater than 1 or when it's less than -1. Okay, so now we have to ask ourselves, what is a restriction on a variable? So I drew in these two number lines to really help us see when is this logarithmic expression defined. So in order for this entire expression to be defined, the first logarithmic term must be defined, and the second logarithmic term must be defined. If any of one of these is undefined, then the whole expression is undefined. So the first one is defined when x is greater than 1, and the second one is defined when it's less than -1 or greater than 1. So you remember, you need both of these logarithmic terms to be defined. So you need both of these number lines to be highlighted simultaneously. So that means the restriction on x, hopefully you can agree that x is greater than 1. x must be greater than 1. Because if it's less than negative 1, only the second logarithmic term is defined. And the first one is undefined. You can't have undefined minus 7, for example. So that doesn't work out. Okay, so let's go with this one. Hopefully your factoring is not that bad. So 2, 1, plus, plus. And this one is 2x, 3x. You need a 1, 1. You want plus 3 minus 2. And then we are going to get log of x plus 2 over 3x minus 1. So that part, to me, the factoring, the common factors, that part's the easy part. The hard part is the restrictions. So I'm going to give myself the number line one more time. So this one, I'm going to do a number line, and the next one is another number line. So I forgot here for my other example, this second number line is for x squared minus 1. Okay? So 2x squared plus 5x plus 2. When is this positive? I'm going to show it on the number line. When it's less than negative half, or, I didn't realize, less than negative 2 and greater than 1/2, sorry. The zeros are negative half and negative 2. So if you draw on the parabola for yourself, you should get this. And for this one, and of course line up the numbers. So this one has zeros of negative half and 1/3. Negative half. If you're having trouble following along with my number line, then give yourself the graph. Because I am technically envisioning the open up parabola in both circumstances. But really what you're doing to find out the values of x which are acceptable is you're really solving a quadratic inequality, which is something you did in the second unit. Anyways, okay. When is everybody happy? When are both logarithmic terms defined? Well, hopefully you can see, I can even draw dashed lines here. Let me sketch this out. Okay, so when restrictions, so x is less than negative 2, or when x is greater than 1/3. Okay, based on what the number lines are showing me, they're both going to be defined, both terms are defined when x is less than negative 2, here and here, or when x is greater than 1/3. Alright, so we got 3 terms here, no problem. We just have to make sure all 3 terms check out. Ooh, if you factor this, I'm going to save myself some time. What multiplies a negative 3? Oh, wait a second, it doesn't work. Oh, I was supposed to make it work. That's my typo. I wanted to simplify to 1, log 1. Anyways, it was my fault. So, we're going to live with that, and we're going to live with something that really can't be simplified. Right? This simple trinomial can't be factored. Negative 3 multiplied negative 3 now to negative 1. I should have made this to be negative 2x. But anyways, you know what? That, like I said, the hard part is really determining the restrictions. So my first number line will be for my first term, x plus 1. When is that positive? When x is greater than negative 1. Okay, what about my second term? When x is greater than 3. Oh boy, what about the third term? Well, because it's not factorable, let me check the discriminant really quickly in my head. 1 minus 4ac. 1 minus 4. Yeah, it is. There are 2 roots. We just gotta find them. Oh, not pretty. So, I'm going to just punch in the quadratic formula very quickly. So negative b plus minus square root of b squared minus 4ac. Definitely not my intention, but you know what? It's working out to be very nice. So that's 4 3's 12, 13. Okay, so 1 minus root 13 all over 2. Let's calculate the numerical value just to double check. 1 minus root 13 all over 2. That's just less than negative 1. Okay. Well, anyways, if you look at the number lines, this value is pretty useless, to be honest with you, because we're definitely in the undefined territory for the other two terms. So this is 1 minus root 13 all over 2. And the other one's 1 plus root 13 all over 2, which is just less than 3. It's 2.3 about. 1 plus root 13 all over 2. So guess what? The restrictions. X is greater than 3. Okay, so really the restriction part is the hard part, because you're essentially solving a bunch of inequalities to determine when is the logarithmic function defined. All right. So we added 2 more tools to our skill set, the product law of logarithms and quotient law of logarithms, which is very much related to the product law of exponents and quotient law of exponents.